The Excel financial functions have been made available to execute a variety of financial calculations, including calculations of yield, investment valuations, interest rates, rate of return, asset depreciation, and payments. However, in this video, we shall be focusing on two particular categories, which are functions relating to our investments and functions relating to our payments and loans. I have shortlisted 8 different functions under these two categories, and I shall be covering them in 2 different parts. These functions are very helpful while formulating an investment plan and assist greatly while making the final investment choices. On the other hand, these functions help us in selecting the best options while arranging finances whenever the need arises. If we were to manually calculate these functions, either mathematically or using basic Excel, it is not a very simple task and can be quite time consuming, thus further emphasizing the importance of Excel's built-in functions. Hi, I am Pratap Narula, investment consultant and educator, and if you like my video, please put in your likes and subscribe to my channel. Also, ring that bell to get all future notifications from this channel and put in your feedbacks and comments. Further, put in your questions in the comment box and I shall get back to you on the same. So let's begin with the very first function, which is the FV or the future value function. The Excel FV function calculates the future value of an investment with periodic constant payments and a constant interest rate. So, for example, like in a recurring deposit account, if you are investing a certain amount of money every month or every year for a fixed period at a particular rate of interest, this function helps you calculate the final amount on completion of the investment term. Now coming to the syntax of this function, this is equal to FV followed by 5 different arguments within brackets. The first of these arguments is the rate or the interest rate per period. The next argument is NPER or the number of periods for the lifetime of the annuity or the investment term. The third argument is PMT or payment, which is an optional argument that specifies the payment per period. Note that if the payment argument is omitted, it uses the default value 0. The fourth argument is again an optional argument, which is PV, that specifies the present value or the lump sum amount that a series of future payments is worth now. Again, if the PV argument is omitted, it takes on the default value 0. The last of the arguments is type, which is again an optional argument that defines whether the payment is made at the start or at the end of the period. The type argument can have the value 0 or 1, where 0 means the payment is made at the end of the period and 1 means the payment is made at the start of the period. If the type argument is omitted, it takes on the default value of 0, denoting payments made at the end of the period. So now let's take up an example where we calculate the future value using the formula that we have just discussed. In the example before us, we have a present value or a starting value of rupees 10,000 with which we have started the investment, and we pay a monthly payment of rupees 10,000 for the next 5 years payable monthly, which makes it a total of 60 payment periods. The interest rate is 10% annually, so for a monthly interest rate we divide it by 12, which gives us a monthly interest rate of 0.83%. Now before calculating the future value using the FV function, please have a look at this chart where I have already calculated the future value using basic spreadsheet calculations. Here we have an opening value of 10,000 as already explained, with an interest rate of 0.3% per month. So at the end of the month we get an interest of 83 rupees in the first month. So the closing amount turns out to be 10,083, which is 10,000 plus 83, which is the interest. At the end of the first period, which is the first month, we pay the first monthly payment of rupees 10,000, which gives us a closing value of 20,083 rupees. Now this value becomes the opening value for the next month. Again, the interest at the same rate of 0.83% gets added on to that, which is 167 rupees, giving it a total of 20,250, at the end of the month plus the monthly payment of 10,000, which gives it a total of 30,250. So if we repeat the same pattern for the next 60 months, we get a final figure of 7,90,823, which is the final amount that we get if we were to pay 10,000 rupees monthly, starting with a opening balance of 10,000 at an annual rate of 10%, which is compounded monthly. For convenience sake, I have copied the same amount out here in this cell, which is 7,90,823 rupees. Now let's come to calculating the same amount using the future value function. We have three ways to get to the future value formula or all the other financial formulas. The first one is by clicking on the formulas tab. Under the formula section, we then click on the financial tab, and under the financial section, we have the FV function. So this opens up the FV function. I'll cancel that and we look at the second way of doing it, where we start typing equal to followed by FV, and the FV function shows up here. We double click and the brackets open up, allowing us to make the entries. To get it back into the tabular form, you can just click on the FX key out here in the formula bar, and again the function arguments open up. The third option is by directly clicking on the FX key and choosing the financial options, and under the financial option we click on F, which takes us to the FV key, and again the argument box opens up. So these are the three different ways by which you can reach out to your required formula. So let's begin with the calculations for this example, and I start by clicking on the financial tab, and from there I click on the FV function key and the argument box opens up. So for the rate, we have 10% annually, so we can either divide 10% by 12 or directly click on the cell which is where it is already calculated. This gives us the interest rate. The number of periods are 60, which we have already shown, so we just click on the cell which gives that number. The monthly payment, PMT, or the monthly payment is 10,000 rupees, but since it is a payment, we need to put in the minus sign first. Whenever you are making any payment, you need to put in a minus sign. In case you are receiving any amount, you don't need to put in the negative sign. So we click on the monthly payment cell, which is rupees 10,000. Again, the present value or the starting value is also 10,000, which has been paid for. So again, first the negative sign and then the present value cell. Okay. Now coming to type, we have two options, either 1 or 0. 1 means the payment is made at the beginning of the period, which is not so in our example. And the second option is 0, where the payment is made at the end of the period. In case you leave out the type section blank, then this will take the default value of 0 or payment at the end of the period. So in our case, we leave the type section blank and we click on OK. Now this gives us a value of 7,90,823, which is identical to the value that we had calculated through the table that I had shown you earlier. Just to check the exact difference, I will subtract one value from the other to see what level of difference there is, and this gives an absolutely zero difference. So this is how we can arrive at the future value, which we can calculate by a very simple FV function, where if we would have actually done it with the help of a basic spreadsheet table, it might have been quite confusing and would have taken definitely a lot more time. On the other hand, once you get used to using these functions, this calculation should not take you more than a few seconds. Next, we look at the PDURATION function. This function calculates the number of periods required for an investment to reach a desired value, again assuming a constant interest rate. Note that this function was only introduced in Excel 2013 and so is not available in earlier versions of Excel. This function is very useful when you want to find out the time a lump sum investment will take to reach a desired value, assuming a constant interest rate like a fixed deposit. The syntax of this function is equal to P duration followed by three very basic arguments within brackets. These arguments are rate, which is the interest rate per period, PV, which is the present value of the investment or the starting value, FV, which is the required future value of the investment or the investment goal. So by using three very basic arguments, you can arrive at the time required to get to a targeted future value of your investments. Let's now look at an example where we can see how to use the PDURATION function to calculate the number of periods required to achieve our targeted goal, considering a fixed rate of interest. So in this example, we have a present value or a starting investment of 2.5 lakhs, which is the lump sum investment that I have made in the beginning. And we have a rate of interest of 9.05%, which stays constant throughout. The target goal that I want to achieve is 20 lakhs. And we shall use P duration to calculate the number of years that I will require to achieve the target goal. But before I start on with the calculations, let's look at the table that I have made in front of you. Here again, I have done the manual worksheet calculations, trying to explain how many years it will take to achieve the targeted goal, which we shall cross-check by using the PDURATION function. So we have a starting lump sum investment of 2.5 lakhs and an interest rate of 9.05% every year. So if you look at the first year, we have an interest of 22,625 rupees, which gives us a closing total of 2,72,625 after adding the yearly interest. So similarly, if we keep on adding the interest for every year and moving downwards, we see that by the end of the 24th year, we have achieved more than 99% of our required target. Or to look at the exact calculation, we need slightly more than 24 years to achieve our target of 20 lakhs. Now let's look at how we use the PDURATION function to achieve this figure in a much more simpler manner. So we start by clicking on the Formulas tab, then on the Financial tab. Here we scroll down to the PDURATION function and we select that function. Under the rate argument, we select the interest rate, which is 9.05%. Under the present value, we select the cell containing the initial value of 2.5 lakhs. And under the future value, we select the cell containing the final goal or the target value of 20 lakhs. And then we click on OK. So this gives us the solution of 24.002 years. And the solution that I had worked out by doing the manual calculations on the worksheet gave us a solution of 24.004. So the difference that you can see between the two methods used for calculations is 0.002%, which I think most of us do not even consider going to a third level decimal. So you can see how effective PDURATION function is and how easily you can get to the solution. Moving on to the next function, which is the NPER or number of periods function. This function calculates the number of payment periods that are required to pay off a loan or reach an investment goal through regular periodic payments and at a fixed interest rate. By using this function, you can calculate the number of periods required to reach a target investment amount, and it can also be used to get the number of repayment periods for a loan that we wish to take. The basic difference between the PDURATION function and the NPER function is that the NPER function calculates the number of periods for a series of cash flows like a systematic investment plan, whereas PDURATION calculates the number of periods for a single lump sum investment to achieve a certain amount like a fixed deposit. The syntax of this function is equal to NPER followed by 5 different arguments within brackets. I won't be explaining these arguments this time, as I have already explained all of these as a part of the syntax in the previous formulas. Now, using the NPER function, let us look at an example where we calculate the loan repayment period for a particular loan amount, and there is a fixed EMI amount to be paid every month, and the rate of interest that is being applied is also constant throughout the period of the loan, which is 9.67% annually. The EMI is being paid on a monthly basis, so the rate of interest is also divided by 12 to arrive at the monthly interest rate. And before we get down to calculating the total repayment term, let us look at the table that we have in front of us, where, like in the previous examples, I have worked out the loan repayment period and how much time it will finally take us to totally repay back the loan. So here we have a starting loan amount of 10 lakh rupees and the rate of interest applied per month is 0.806%. So at the end of the first month, 8,058 rupees is added to the total outstanding, which makes it a total outstanding of 10,08,058 rupees. At the end of the first month, the first EMI of 15,000 is paid, which gives us a closing balance of 9,93,058 at the end of the first month. In the same pattern, if we continue to move downwards, where the monthly interest is added and the monthly EMI is paid, so we move further down just to check where we wind off with the loan repayment schedule. And at the end of the 96th month, we are left with a total outstanding of 16 rupees, which I would say is quite negligible considering the total loan outstanding of 10 lakh rupees. So I can safely assume that after 96 months, we have totally repaid back our loan. Now let's get back to our example and let's see how we can calculate the same using the NPER function. So I'll start with the formula, and this time I will not click on the tabs. Instead, I will start the formula directly by typing equal to followed by NPER, and we have the function out here. I double click on NPER and I have the 5 arguments in front of me, which I can also expand by clicking on the FX key, and the table opens up out here. So under the rate section, I select the cell which contains the monthly rate, and under the payment section, first I put in the negative sign since we are making a payment from our end, and then I select the monthly payment amount. Under the present value, I select the cell which contains the total outstanding of the loan right in the beginning, which is 10 lakh rupees. Under the future value, I would ideally put in the amount which I am targeting at the end of the repayment period, which is 0. So I don't need to make any entry, as by default it assumes a 0 value if no entry has been made. Under the type criteria, again here if you do not make any entry, it assumes that the payment is made at the end of every period, which is so in the case that we are explaining. So I don't make any entries in the last 2 arguments and I click on OK. And we get the answer which says 96.001. 0.001 because 16 rupees is left off at the end of the payment term, which needs slightly more than 96 months, which is a very negligible portion. So here we can see that the data contained in this entire table to try and work out as to how long it will take to pay back a loan with a fixed EMI and with a fixed rate of interest is solved so easily by just putting in one of the built-in formulas offered by Excel, and it gives us an immediate solution. Another useful function for our personal analysis is the rate function. This function calculates the interest rate required to pay off a specified amount of a loan or to reach a target amount on an investment over a given period. This will be applicable for a constant periodic payment. This function is usually used to calculate the interest rate per period of an annuity plan. For this function, the syntax is equal to rate followed by 6 different arguments within brackets. Let us look at the last argument, which is guess, as this has not been covered before. This is an initial estimate of what the rate will be. If this argument is omitted, it will take on the default value of 10%. This is only a starting value for Excel to start working with, post which it arrives at the correct rate using its built-in procedure. In the following example, where I shall be explaining the rate function, we have a scenario of an investment plan where the initial or the present value, that is the lump sum deposited in the beginning, is 45,000 rupees, and there is a monthly payment of 12,500 rupees, which finally matures to a value of 10 lakh rupees after a continuous payment of 60 months. Now with the help of the rate function, we shall be checking what is the rate of interest that has been provided by this investment plan. Although you can see that the rate of interest which has been provided is 8.53%, which has been divided by 12 to get it on a monthly basis. This information has been provided so that we can cross-check the value arrived at by using the rate function. First, I'll just quickly explain the table where we have a starting value of rupees 45,000. The monthly interest is 0.711%, and the interest received at the end of the first month is rupees 320, which is added to the initial value of 45,000. Further, the monthly payment at the end of the month of rupees 12,500 has been added to this value, which gives us a closing value of 57,820. So if we move down the table for a period of 60 months and we come to the last month, we see that the final value is rupees 10 lakh and 92 rupees. 92 being a slightly excess amount, which again is very negligible considering the total target that we have arrived at. So now let's go back up to our example and calculate the rate of interest that we want to check, which has been applied to this investment plan. So we start with the formula, and after we enter rate, we have the rate function below. We double click, and here we have the 6 different arguments that I had talked about. Guess being the new argument, where we have to put in an approximate percentage that we feel is the correct amount, or we can leave it blank, where the computer will take a default value of 10%. So this time I won't open the argument box and I will make the entries directly in the formula itself. So the first argument is NPER, which is the number of periods, which we have available to us as 60. So we click on this cell. After that, since we are typing directly, we put in a comma. Next, we move on to the argument of payment. That is the monthly payment that we are making for the investment plan. So first, since we are making the payment, we put in a negative sign and followed by 12,500, the cell which contains this value. We click on that. Again, we put in a comma. Next, we have to come to the present value. The present value is the lump sum that we've already invested. So again, we made that payment. So we put in a negative sign. Then we come to the cell which contains this value. That is 45,000. We click here. Next, we move on to the future value. That is our target value, which is 10 lakhs. So we click on the cell containing that value. And further, we come to type. Now again, in this example, type, even if we do not put in any entry, we get the option of end of the period, or we can put in 0. So either of the entries. This you can see is displayed just below the formula also. That's 0, which means end of the period, and 1 means beginning of the period. So I leave this blank. So if I have to leave this blank when I'm directly typing a formula, I just put in another comma sign, which will bypass this argument. And then we come to the last argument, which says guess, which is guessing the approximate interest rate that is being offered on this investment plan. So let's assume we exactly don't know what is the interest rate being offered, and I put in 9%. And after this, I close the bracket and I press the enter key. Here you see we have 0.711%, which exactly matches the monthly interest rate that is being provided. So here we see that using the rate formula, we can easily arrive at the interest rate that is being offered by a particular deposit plan. However, here I would like to add that constant periodic payments are not a real life scenario, because investment cash flows, be it in or out, are never evenly spaced out. Sometimes there are late deposits or early withdrawals. Sometimes a couple of months are skipped in a row, and in such cases, calculating the returns from investment becomes difficult. For such situations, we have the XIRR function, or extended internal rate of return, which is a measure of return that is used when multiple investments have been made at different points of time in a financial instrument like mutual funds. It is a single rate of return when applied to all transactions, investments and redemptions would give the current rate of return and can be calculated only in Excel. I have already covered this in one of my previous videos, and the link for this is available on the top of your screens and in the description below. I would request you all to please go through this video, as this is a very important function which gives us the real-time return on our investments. This brings us to the end of part 1 on my videos on financial functions. Hope you enjoyed it. I shall be back soon with part 2. Till then, Happy watching, and I would once again request you all to like and subscribe to my channel.